All right, so one of the things that you would have had to looked up, or maybe you kind of figured it out on your homework, are these preparation of epoxide reactions. These are pretty straightforward, but nonetheless, we prepare epoxides starting with alkenes. And there's two different ways to do it that are perfectly equivalent. They both give you the exact same product no matter what reactant you start out with. The first is by doing this reaction with bromine and water to create what's called a halohydrin. This would have been one of the reactions of alkenes that you covered. And then if you treat that halohydrin with sodium hydroxide, you will get an epoxide. Or you could use something a little bit fancier, what's called MCPBA. And we'll talk a little bit about this here in a second, but that is also just going to give you that exact same epoxide product from an alkene. All right, so MCPBA here, what the heck is that? This is what's called a peroxy acid. And it must just be an especially stable peroxy acid, because you could really use any peroxy acid to create an alkene, but much like epoxides, they're very reactive, so this must just be like the preferred one because it's got a nice stable shelf life. All right, we can draw out the structure here. All right. Importantly, stands for meta. You don't have to know this, but just so you, for FYI, metachloroperoxy benzoic acid. And again, that peroxy acid is kind of the important part. So first of all, I'm going to put a chloro group meta to this acidic group. All right, but it's not just a carboxylic acid, which would have an OH right here, but a peroxy acid, which has this OH bond. So it's like we stuck an oxygen in the middle of our carbonyl and our hydroxyl group for our carboxylic acid. You might have heard of peroxides before. Hydrogen peroxides got that same basic structure, where again we have two oxygens linked together. This is H2O2 or hydrogen peroxide. All right, these structures might jump out at you as looking kind of weird. They don't violate any of our bonding rules, right? Oxygen has two bonds and two lone pairs. They're legit like that. If you remember from general chemistry how to calculate oxidation numbers, the weird thing about these complexes is that our oxygens have an oxidation number of -1, and oxygen loves to have an oxidation number of -2. So these are used a lot as oxidation agents. They're really good at accepting electrons, okay? Importantly, our peroxy acid, what's going to happen is this little weird oxygen right here is going to end up inserting itself between that carbon-carbon bond to form our epoxide. Okay? So when you use your peroxy acid, you get MCPBA plus a carboxylic acid. All right? It loses that extra oxygen. And I guess just to note, this one has this really weird formula. We're used to carboxylic acids being COOH, right? This would be COOOH for our peroxy acid. You don't have to know the structure, but just fun fact. We just call it an MCPBA. But that's what that little acronym stands for. All right. Our other method here is one that we're going to look at a little bit more closely. All right, again, we're going to take our alkene. If we treat it with bromine in the presence of water, right? If you just treat an alkene with bromine, you get a bromine on either side. But if we treat it with bromine in the presence of water, we get this thing here, what's called a halohydrin. And then by treating your halohydrin with sodium hydroxide, you create your epoxide. It's going to drive me nuts. Okay, so we're going to take a look at this step in particular. That last step. I'm going to zoom in here. All right, and we're going to try to do the mechanism of this step here. All right, let's think about it. Would this be an acidic or a basic condition mechanism? Basic, because we got that sodium hydroxide there. So remember, under basic conditions, we shouldn't have any positive charges, but we're allowed to have other strong bases, so we're allowed to have negative charges. All right? So I'll tell you that there is just one more step in our mechanism, or rather one missing intermediate. We got 2 steps to fill in electron pushing arrows. Okay? The other thing that I'm going to note before I want you guys to try this on your own here is what else do we know about these halogens? Exactly. Unlike our hydroxyl groups, which we had a pain in the butt getting rid of, these halogens are very easy to get rid of. They are good leaving groups. All right, so I want you to pay attention to what new bonds are being formed in your products, what bonds are being broken on your reactant side, and see if you can't give me the mechanism for this ring closing reaction to form this epoxide here. So let's see if we can't reason through this. Okay, importantly, we're going to have to break a few bonds on our reactant side. We're going to have to break this bond and this bond, right? And I need to form a new carbon-oxygen bond. So I need to form a bond between these ones here, right? That's what my mechanism should accomplish, breaking those two bonds and forming that one new bond. Cool, all right. So first of all, I can't just kick off my leaving group right here and be done with it, right? I'm not going to form a primary carbocation, okay? But we could have our nucleophile attack and our leaving group leave all in the same step, right? Form that new bond there and kick off that leaving group all in one step. So let's draw our products here and see if this is legit. This would be my intermediate here. Is this going to be allowed under basic conditions? No, this is way too strong of an acid here. This protonated oxygen is way too strong of an acid to survive under basic conditions. So, can't do that first, but remember, when we need to manage our charges, we have these proton transfer steps that we can do. If I deprotonate that oxygen first, then I won't have that same problem. And this is basic conditions. So I have my proton acceptor, my hydroxide ion. Importantly, I don't remember if I've said this before or not, but whenever I see something like sodium hydroxide, whenever I see a metal ion in there, I just blur my eyes and I erase that metal ion and I put in a negative charge because the sodium is never doing a damn thing. It is just floating around as a counter ion in that solution. It's really the hydroxide that's going to be important in this reaction, the one playing the role of the base. So first I'm going to do a proton transfer step, meaning I'm going to take that proton off of that oxygen. And now if I do my nucleophile attacking and my leaving group leaving all in one step, I don't have any sort of breaking of the rules of my basic conditions. Importantly, this intermediate is perfectly fine under basic conditions. My deprotonated oxygen, perfectly fine under basic conditions. So we're going to have that new bond form and kick off that leaving group to form our epoxide ion. Right? So in this reaction here, we create this what's called halohydrin, which has this hydroxyl group located right next door to a good leaving group, that bromine. We then deprotonate that hydroxyl group, creating this good nucleophile, which is going to attack its next door neighbor, forming this ring closing reaction, forming our epoxide here. Cool. All right, and again, there's really no difference between using these two. I mean, I gotta say, one of these is way cheaper to do than the other one. But I will tell you, having attempted to execute this in the lab, it's also a huge pain in the ass. Bromine and water don't mix very well together. You got to use like a ridiculous amount more of this solution. Anyways, it's just kind of a pain. I can understand why they would go for the more expensive but more efficient route here. But both of these would give you the same epoxide product. There's no difference between these two reactions, other than cost. All right, so last thing we got to cover for epoxides is everybody's favorite, the stereochemistry of these epoxide reactions. All right, so we kind of glossed over any sort of stereochemical consideration just so we could make sure that we had our basics of what was going on in these reactions, these ring opening reactions, as well as the difference between our acidic and our basic conditions, right? We talked about how those different conditions affect the regioselectivity of these reactions. But now we need to talk about stereochemistry, okay? So let's start out with a cyclic alkene. And let's make our epoxide here. All right, so if we use our straight line bonds, this is kind of a lie. Because when you use those straight line bonds, you're implying that you get a mixture of all possible different stereoisomers, right? Meaning I would get a mixture of both my cis stereoisomer, where both of these bonds are pointed on the same side, as well as my trans stereoisomer, where these bonds are pointed on opposite sides. And one of these structures just doesn't make any sense. All right, which one of these is the correct structure? The one on the left or the one on the right? All right, let's think about it. If both of these bonds are pointing in the same direction, that means that this bond and this bond are both holding on to that oxygen atom. If they're pointed on opposite sides, that means that this bond and this bond are both holding on to the same oxygen atom, right? Which one of those is feasible? The one on the left or the one on the right? This is the only one that you could possibly have. You can't have bonds pointed on opposite sides that are holding on to that same atom. They're spatially pointed in different directions, right? So you're only going to get one of these two. So we can't use our straight line bonds because it's kind of a lie. It's implying we have both of these, and we don't have both of these. We have one very specific stereoisomer here that we get. Cool. So, importantly, when we form our epoxide, we only get that cis stereoisomer. Okay, so then let's take this and let's treat it with one of our nucleophiles. And let's think about it. It's going to attack one of these carbons in my structure here, in my epoxide. But let's think about the direction in which it's going to attack from. Is it going to be able to attack from the same side as that leaving group, or is it going to have to attack from the opposite side of where that leaving group is? It's got to attack from the opposite side. The leaving group's just straight up in the way if it tries to attack from that same side. So it's going to attack specifically from the opposite side, which is going to lead us to a stereospecific product. Well, crap. I'll have my one hydroxyl group on a wedged bond, but my other hydroxyl group on a dashed bond. All right? And importantly, we have this stereospecific product here because my leaving group has to be on the opposite side of where that nucleophile is attached. All right? So our nucleophile is added to the opposite side of that epoxide ring. okay? And if I was being really good, I would also draw my other enantiomer here. I will tell you on your homework, as long as you give me one of the two, you're fine. You don't have to draw them both. Okay, all right, so let's practice this real quick. Again, we've kind of not been treating these as stereospecific reactions, but just by nature of these rings and how they're formed, they have to form on the same side. Those two bonds making my triangle have to be pointed in the same direction. So we, given a ring, we're going to get a stereospecific product here. Cool. All right, so let's just do another one. First, you're going to make your peroxide, then you're going to treat it with this alkoxide ion, this propoxide ion. So just to be clear, I'm going to break this up into these two steps here. After that first step, when we form our epoxide, our bonds to that oxygen have to be pointing in the same direction. Previously, I used two wedge bonds. Now I'm going to use two dash bonds. Either one would be fine, right? We're going to get a mixture of both of them. But importantly, after that second reaction, my nucleophile will have attacked from the opposite side of where that epoxide ring is. So my nucleophile is going to be joined as a wedged bond pointed in the opposite direction, whereas that hydroxyl group from my epoxide will be on a dashed bond. And if you had your dashes and wedges switched, that'd be perfectly fine, right? Your hydroxyl group could be on a wedge, and your ether group on a dash, that's perfectly fine as well. That would just be the enantiomer of this structure here. Again, I'll only ask you for one of the two. If we are being really good, what you'll see in your textbook is they say plus En, plus the enantiomer. All right, cool. So that's all well and good for ring structures. I think it's a little bit easier to imagine for ring structures here because of this sort of intermediate, the idea that you can't form an epoxide when you have two bonds pointed in opposite directions. I think that kind of just checks out mentally, all right? But you are also going to see this stereospecificity with other alkenes as well. All right, let's think about this. We're going to take two different alkenes. one in the trans conformation, and one in the cis conformation. And we're going to treat them both with that peroxy acid. All right, I'm going to take this example first, because in order to kind of visualize this a little bit better, we're going to rotate this structure here. Right? I'm going to take this thing and flip it 90 degrees as if I'm looking at it like this, and now I want to look at it like this. All right? If I look at it on its side, I have one bond pointing into the page and this other bond sticking out of the page. Right? I just took that alkene and rotated it here. And importantly, when my epoxide forms, again, that triangle, those two bonds have to be on the same side. So I'm either going to stick my oxygen on top here or on the bottom here, but regardless, this is going to lead to this stereospecific product where I have my triangle, all these straight line bonds, but now I have this group pointed away and this other group sticking out at me. Right? So we get this stereospecific epoxide that forms from our alkene. So in your weekend homework assignment, it was like, hey, just ignore stereochemistry for this assignment, right? We were kind of glossing over this complication here. So that would be my product if I started out with that trans 2-butene. Everybody take a second and see if you can't give me my product if we started out with the cis 2-butene. All right, and again, the way that we're going to draw this, it's by far the easiest way to draw this, is we're going to keep that epoxide within the plane of the page. Right? I need to know whether these bonds are going to be sticking out at me or pointing into the page. That's the question. These two methyl groups here. So, the nice thing about the stereochemistry of these epoxide reactions, we can say epoxide formation preserves stereochemistry. Which means that if I start out with a trans alkene, I'm going to get a trans epoxide, where those two groups are pointed on opposite sides. Likewise, if I start out with a cis alkene, I'm going to get a cis epoxide, where those two groups are again pointed on the same side. So whether you do two wedges or two dashes are equivalent, but importantly, they got to be the same. All right, I start out with a cis alkene, I get a cis epoxide. All right, so let's see if we can extend this analogy to something a little bit more complicated here. we'll leave this up here for reference. Just for the sake of variety, we'll use our different method, the hydrohalogen method, treating that with NaOH. Again, in terms of your product formation, there's not really anything different you have to consider for these two reagents. So I'm going to keep track of my carbons here. This will be the blue carbon. This will be the red carbon. All right, and when I drew my product, I drew it so that these two bonds were in the plane of the page. So now I got to show the other bonds, okay? And importantly, if I look here in my structure, the methyl group on my blue carbon and the ethyl group on my red carbon are pointed in the same direction about that double bond. That means when I draw my epoxide, they better be pointed in the same direction. They either both are going to be on a wedge or both are going to be on a dash. Whichever one you pick doesn't matter. I'm going to pick a wedge. So I'm going to put this methyl group on a wedge. And again, since that's pointed in the same direction as those carbons on that red carbon, I'm going to have to put that on a wedge as well. Boom. And then lastly, I need that other set of carbons on my blue, those other two carbons. So those are going to be on a dashed bond. And just to be clear, if you had the exact opposite of this, it's an enantiomer, that would be perfectly fine as well. Either these bonds on a dash, and this bond on a wedge. That's fine too. All right, either one of those are acceptable. But importantly, these two groups, they're on the same side of my alkene. So those two groups better be on the same side in my epoxide. Cool. So these epoxides, because they are these three-membered rings, they form in this stereo-specific way. All right? And that's going to have a consequence for the reaction of these epoxides. So let's start simple here. Let's take this one here. And now we're going to do a follow-up reaction where we treat that with one of our nucleophiles. And remember, when that nucleophile attacks, it has to do it from the opposite side of where that leaving group is, right? That ring opening reaction. So, my new bond, without even paying attention to my wedges here, I'm going to draw my hydroxyl group from my epoxide and my nucleophile. They have to be pointed in opposite directions. All right, and now I'm going to fill in my stereospecific methyl groups here. This one was on a wedge, pointed out at me. The other one is also still on a wedge. It just got bumped up because of that leaving group, or rather because of that nucleophile. So here is my stereospecific product of this ring opening reaction, starting with my stereospecific epoxide. All right, let me just be clear about what is not correct. I have a feeling, just because of the ease of the copying and pasting on our homework here, that a lot of people will be tempted to give me this structure. All right, this is not correct. You could go in and you could assign RS stereochemistry, and you would see that these are indeed distinct structures here. All right, this is just not accurately reflecting the stereochemistry of our epoxide product, because it doesn't show the nucleophile attacks from the opposite side. That's what you would draw if the nucleophile attacked from the same side, right? So it does not correctly convey our stereochemistry of our epoxide reactions. All right, so let's take our other one. And then we'll do our more complicated one after this. All right, I want y'all to take a second. Here's what we got for our first step. Now let's treat this thing with one of our nucleophiles. Whoa. All right, so importantly, when I'm drawing my product, my stereospecific product of these epoxide reactions, the first bonds I'm going to put in are my hydroxyl group for my epoxide, my 2 carbons, and that added nucleophile pointed on opposite sides of one another. All right, and now I just have to fill in my dashes and wedges just like in my epoxide. This is going to be a wedged bond still. And my other methyl group is also going to remain a dashed bond. I just got to move it up. Now it's pointed up in space. Okay? Right? So again, we start out with the zigzag, bump, bump, bump. with our hydroxyl group and our nucleophile added 2 carbons apart. Important, those have to be pointed on opposite sides here. Again, I can't do this, I guess just to be clear, looking at this bottom structure, there's nothing illegal about my bond line structure rules. This is a perfectly legitimate bond line structure. It's just got the wrong stereochemistry. I just haven't correctly shown the stereochemistry of my product because I have my hydroxyl group and my nucleophile on the same side of that molecule. They need to be pointed on opposite sides. All right, so again, this is not correct. So let's just stack these two next to each other so we can see. Let me get rid of all these little markings. All right, if we start out with our cis alkene, we get a cis epoxide, which is going to lead to this stereospecific product here. And if we start out with a trans alkene, we're going to get a trans epoxide. Oh, and I don't know why I put an NH2 on the bottom there, my bad. Wrong nucleophile. Boom. Sorry if that was confusing. It's like, where did the nitrogen come from? Okay, my bad. All right, and importantly in both of these here, just note, I started by drawing these carbons here in the same plane, right? One with the hydroxyl group pointed up, one with my nucleophile pointed down, and then I just decorated with these stereospecific carbons. If they were on wedges before, they're going to be on wedges on my product, and if they were on dashes before, they're going to be on dashes in my product. All right, so now let's just see if we can't, from the beginning, we'll use our more pain in the butt one here. Treat this thing with an alkoxide ion. We already did our epoxide here. And draw that in. And then see if you can't get our stereospecific product of this reaction. All right, and importantly, not only do we have to worry about the stereospecificity, but also the regiospecificity. Remember, my nucleophile is going to prefer one of these two carbons, either the red carbon or the blue carbon, because of that stereospecificity that we talked, because that regiospecificity we talked about last class. All right, so if I draw my epoxide, so if I'm going to start out here, here's my blue carbon, here's my red carbon. Which one should have that nucleophile on it? Let's take a step back. Is this a basic nucleophile or an acidic nucleophile? Definitely a basic nucleophile. So is it going to prefer the tertiary carbon, the blue one, or is it going to prefer the more accessible secondary carbon? In this case, because it's a basic nucleophile, it's just basic always prefers what's more accessible. So my nucleophile, I'm going to add to that red carbon. My hydroxyl group will be on that blue carbon. If this was an acidic nucleophile, then it prefers the tertiary for that really weird reason we talked about last time, right? But in general, basic nucleophiles always the more accessible. And now I need to make sure to put in those stereospecific alkyl groups. On that red carbon, I had this ethyl group on a dash. That means I need to put in that ethyl group on a dash, right? We don't flip our dashes and wedges or anything like that. After you've got your epoxide, you've got the hard part down. Same thing over here, I need to put in my, now it's a methyl group on a dash. We got this ethyl group on a wedge. Boom. So there's my stereospecific product. And if you gave me the enantiomer, which means that all of your wedges were dashes and all of your dashes were wedges, that'd be perfectly fine as well. Okay, one more thing real quick that I just want to point out that is illegal with regard to drawing bond line structures is trying to put like your wedge on the opposite side of where your dash is. This is just illegal from the bond line structure standpoint. It's not even like your stereochemistry is wrong. It's just this cannot happen. You can never take a tetrahedral and orient it in space such that two bonds like this are lying in the same plane and one's pointed at you and one's pointed away, right? This is just not the correct representation of a tetrahedral. The bottom line is your dashes and wedges have to be together, have to be next to one another. Okay, next, not opposite. Cool. All right, we got one more, what I think is very easy set of reactions to cover for our thiols next time, and then we'll be done with chapter 18 and we'll spend the rest of the week doing some review. Cool. Break.